In this experiment, you will synthesize a transition metal compound chloropenamine cobalt-3 chloride. This compound is a solid at standard conditions, so you will determine a percent yield based on the mass of product formed. Characterization of this substance will be completed using infrared spectrophotometry, or IR. There are two definitions which are fundamental to this experiment. Coordination compounds are those which usually contain a transition metal, such as iron, cobalt, or nickel, and attached groups called ligands. A ligand is a Lewis base which can donate one or more pairs of electrons to form a coordinate covalent bond with the metal, which is a Lewis acid. Both electrons in a coordinate covalent bond are provided by the ligand. Monodentate ligands provide one pair of electrons, and examples are chloride, bromide, water, ammonia, triphenylphosphine, and nitrite. Bidentate ligands provide two pairs of electrons and form two coordinate covalent bonds with a Lewis acid. Typical bidentate ligands are carbonate, ethylene diamine, and the anionic form of acetylacetone. One example of a coordination complex is cis-dichlorotetramine cobalt-3. This complex, which also exists as the trans geometric isomer, has a +1 charge, and like any cation, would require a negatively charged anion to exist as a solid. The Lewis acid in this complex is cobalt-3. There are two different monodentate ligands in the complex: chloride, which has a -1 charge, and ammonia, which is called amine, which is neutral. The molecular geometry of this complex is octahedral. Another example of a complex is tris-oxalato-ferrate 3. The Lewis acid in this complex is iron 3, and it has 3 oxalate bidentate ligands attached to it. The prefix tris indicates that 3 bidentate oxalate ligands are present. The electron pair donor atoms on oxalate are 2 oxygen atoms. Since the charge on each oxalate ligand is -2, and the overall charge of the complex is -3, the charge on iron is +3. This complex has an octahedral molecular geometry. A final example is the octahedral metal complex cis-dichloro-bis-ethylene-diamine cobalt-3. The prefix bis is used instead of di to indicate that 2 of the bidentate ligands, ethylene diamine, are present. The donor atoms on ethylene diamine are 2 nitrogen atoms. The overall charge of this complex is +1. Since chloride has a -1 charge and ethylene diamine is neutral, cobalt has a +3 charge. A very simple reaction which illustrates the effect of a coordination complex on chemical reactivity involves the precipitation of silver chloride. You have seen the reaction of silver ion with chloride ion in both general and organic chemistry labs. For each mole of silver chloride precipitate that's formed, a mole of silver reacts with a mole of chloride. Consider the empirical formula of each cobalt compound in the following series of reactions. Each one contains 1 mole of cobalt and 3 moles of chloride. Each of these formulae suggests that 3 moles of silver ion would react with 1 mole of each cobalt compound. This prediction, however, is not observed experimentally. For 1 mole of the first cobalt compound, 3 moles of silver ion are needed to completely react with chloride, with 3 moles of silver chloride formed. For the second cobalt compound, only 2 moles of silver ion are needed to completely react with chloride. And for the third cobalt compound, only 1 mole of silver ion is needed. Let's summarize these reactions and include color differences on the next slide. Each of these compounds is a different color, the first one yellow, the second purple, and the third green. The molecular formula indicates the bonding in these compounds and what constitutes the coordination complex in each compound. In the yellow compound, only ammonia groups are bonded directly to the cobalt. All 3 chlorides are present as anions in this compound and are available to react with silver ion. The hexaamine cobalt-3 complex is the cation in this cobalt salt and has a +3 charge. In the purple compound, 5 ammonia groups and 1 chloride ion are bonded to the cobalt. The remaining 2 chloride ions can react with silver ion. The pentamine chloride cobalt-3 complex has a +2 charge. The green compound has 4 ammonia groups and 2 chloride ions bonded directly to the cobalt. Only 1 chloride ion can react with silver ion. The tetraamine dichloro cobalt-3 complex has a +1 charge. The color is different among these 3 compounds since the number and types of ligands present in the coordination complex of each one is different. Valence is the maximum number of univalent atoms, such as hydrogen or chloride, that may combine with an atom of the element under consideration. Alfred Werner, a Swiss inorganic chemist who was awarded the Nobel Prize in Chemistry in 1913, stated that most elements exhibit 2 types of valence. Primary valence is now called the oxidation number, and secondary valence is the coordination number. Oxidation number is the charge that results from the gain or loss of electrons in the outer electron level. Coordination number is the number of single bonds formed by the central atom in a coordination complex with ligands. For the coordination complex tetraamine dichlorocobalt-3, the oxidation number of cobalt is +3 since it has lost 3 electrons, and its coordination number is 6 since 6 monodentate ligands are attached to it. The initial reaction in the synthesis of chloropentamine cobalt-3 chloride involves the replacement of the water ligands on cobalt with ammonia ligands, with the oxidation number on cobalt remaining +2. Then, in the presence of ammonium ion and hydrogen peroxide, which is an oxidizing agent, 1 ammonia ligand is temporarily replaced with water, and the cobalt in this coordination complex is oxidized from +2 to +3. A chloride ion, from hydrochloric acid, then replaces the water ligand. The charge on the coordination complex changes from +3 to +2, since the chloride ion carries a -1 charge. The final product is then crystallized from solution using concentrated hydrochloric acid and collected via vacuum filtration. Caution should be exercised when handling 12 molar hydrochloric acid, 15 molar ammonia, and 30% hydrogen peroxide. All can burn your skin, and the acid and base are extremely volatile and very irritating to breathe. Minimize any spillage when handling the 2 solids, cobalt chloride hexahydrate and ammonium chloride. This reaction mixture undergoes a series of color changes when heated, starting with dark purple, then to green, and finally to the light red-violet product. Don't start heating the reaction mixture too soon. Follow the instructions as indicated in the experimental procedure. The final product is washed with cold water, cold ethanol, and finally with ether. Note the progression from polar to nonpolar solvents in this series. This product is characterized by percent yield, color, and infrared spectrum. Operating the infrared spectrometer, or IR, usually does not require running a background. This has normally already been completed prior to the start of the lab period. When storing your product for the next lab period, if it still appears slightly wet, do not attach the cap to the vial. For a product that is very wet, it should be allowed to air dry in a weigh boat. The only waste collected is the filtrate from your filtering flask. Be sure to neutralize any remaining acid in the filtrate with sodium bicarbonate prior to pouring it into the common waste container. All other aqueous waste can be discarded down the drain with cold water. There is no solid waste generated this week. All glassware used in this synthesis can be cleaned with water. No acetone is used. When you are done, rinse the probe with the digital thermometer with cold water and dry it with a towel.